So in this numerical, a transformer rating 200 volts upon 50 volts is given, and it is a 10 kVA transformer, and core loss is given as 100 watts. Okay, so we have to calculate the maximum efficiency of the transformer at 0.8 lagging power factor. Okay, so assume that the full load copper loss is 200 watts. At what load this maximum efficiency is obtained? So in this numerical, iron loss is given as 100 watts and full load copper loss is given as 0.2 kilowatt. Okay, so the load corresponding to maximum efficiency is rated kVA into under root of Pi upon Pc. Okay, so this is the formula to calculate the load corresponding to maximum efficiency. So these values are substituted here. 0.1 and 0.2 is given, so it is substituted to get the answer as 7.07 kVA. So maximum efficiency at 0.8 lagging power factor is power rating into power factor. In the numerator, what we write output power, and output power is what? Vi cos phi, and Vi is the load which we have calculated for maximum efficiency. So it is 7.07 kVA. So cos phi, which is the power factor, it is multiplied by 0.8, and in the denominator it is input. Okay, so input is what? Output plus losses. So output is substituted as it is, plus iron loss, which is 0.1 kilowatt. The losses were given in watts. Okay, they were converted into kilowatt, so they were divided by 1000. Okay, so again this copper loss is given as 0.1. Why? Because at maximum efficiency, iron losses and copper losses are same, and we are calculating this numerical for maximum efficiency. So in this way we can calculate the maximum efficiency at 0.8 lagging power factor. Okay, so second part is that would our answer be different if the power factor were unity? Okay, so everything remains same, but 0.8 is substituted by unity power factor. Now in the next numerical, a 200 kVA transformer has an efficiency of 98% at full load. If the maximum efficiency occurs at 75% of the full load, calculate the efficiency at half load. Assume negligible magnetizing current and power factor is given as 0.8 at all loads. Okay, irrespective of whatever the load it may be, power factor is given as 0.8. Okay, so the full load was given as, rating of the transformer was given as 200 kVA. So Vi cos phi, so the cos phi is 0.8. So the full load output becomes 160 kilowatt. Okay, and full load efficiency is 98%. So when the efficiency is known to us, output is known to us, then we can calculate the input. Okay, because we know the general formula that output upon input is equal to efficiency. Okay, so it is, input is calculated as 163.265 kilowatt. Now the total losses are the iron losses and copper losses, and these losses are the difference of the input minus output. So when we do this difference, we get 3.265 kilowatt. So now this is the sum of the iron loss and copper loss. Okay. Now it is given that if the maximum efficiency is occurring at 75%, okay, it means that at 75%, 75% is what? 3 by 4. So at this efficiency, or 75% of the load, or 3 by 4th of the load, the iron losses and the copper losses will be same. So this is exactly what we have done. So x square pc is equal to pi. So here x is 3 by 4. So it becomes 3 by 4 square pc is equal to pi. So here we get the relationship between the pi and pc. Okay. So one relation is this pi plus pc, and second relation we know that pi plus pc is equal to 3.2. Okay. So two relationships, two unknowns, we will solve them to get the iron loss and copper loss, full load copper loss. Okay. So now in the second part, load is half. Okay. And we have to calculate the efficiency. Okay. So now for the output becomes half into 200 into 0.8. Okay. Because power factor remains same. And the total losses become pi plus x square pc. So 1.175 we have calculated, half square into full load copper loss, that is 0.09. This is calculated as 1.69 kilowatt. So now when the iron losses and the copper losses are known to us, full load losses is known to us. So the efficiency output up is equal to output upon input plus losses, output plus losses. So substituting these values, we get the efficiency. Okay.